Welcome to Jeremy's IT Lab. This is a free complete course for the CCNA. If you like these videos, please subscribe to follow along with the series. Also, please like and leave a comment, and share the video to help spread this free series of videos. Thanks for your help. This video, unlike the last one, is not going to be practical, meaning that you won't actually go on and configure a Cisco router or switch. Also, most of the information in this video won't be new. We've already covered most of it in previous videos. However, I decided to make this video because I think it's very important to make sure you have a good understanding of the complete process a packet goes through when being sent across networks. Hopefully, this video will be a little shorter than the usual ones. Let's get started. So, what will we cover in this video? We'll cover the entire process of sending a packet to a remote destination. This will include things like ARP, encapsulation, de-encapsulation, etc. Of course, there are different levels of depth we can go into when talking about this process, and I won't give unnecessary details that would only be expected of a CCNP or CCIE. But in this video, I hope to give you a solid understanding to get you ready for your CCNA. My hope is that this video will help you put all of the pieces together that we learned previously. So, this is the life of a packet, the process a packet goes through when being sent to remote networks. Here's the network topology we'll use for this video. If you watched Day 11's video, you should recognize this topology, as it's the same one we used to demonstrate static routing. We'll follow a packet being sent from PC1 in the 192.168.1.0/24 network to PC4 in the 192.168.4.0/24 network. Let's assume we have pre-configured static routes on these devices, so that the packet will follow the same path as in the static routing video. That is from PC1 to R1, R2, R4, and then PC4. This doesn't have to be the path the packet takes. The path that goes via R3 instead of R2 is valid too, but we'll stick to the same path as last time. Now, since we're not just looking at layer 3 in this video, let me add MAC addresses for these devices. I'll use 1111 for PC1. Now, as you know, a MAC address is actually 12 hexadecimal characters, but just to save space, I'll shorten them to 4. R1's G02 interface has a MAC address of AAAA, and its G00 interface has a MAC address of BBBB. That's something I didn't mention before. Each interface on a network device has a unique MAC address. Note that Switch 1's interfaces also have MAC addresses. However, for this video, it's not necessary to know the MAC addresses of the switches, so to avoid clutter, I'll leave them out of this diagram. R2 has a MAC address of CCCC on its G00 interface, and DDDD on its G01 interface. R4 has a MAC address of EEEE on its G01 interface, and FFFE on its G02 interface. I didn't make it all Fs because the MAC address of FFFF, 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 12 Fs, is the broadcast MAC address. So just to avoid confusion, I added that E on the end. Finally, PC4 has a MAC address of 4444. Okay, so PC1 wants to send some data to PC4, and it's encapsulated in this IP header. The source is 192.168.1.1, PC1's IP address, and the destination is 192.168.4.1, PC4's IP address. Now, because PC1's IP address is in the 192.168.1.0/24 network, it notices that the address 192.168.4.1 is in a different network. So it knows that it needs to send the packet to its default gateway, which is R1, something we have already pre-configured. However, in this example, PC1 has not sent any traffic yet, so it needs to use ARP, the Address Resolution Protocol, something we covered in a previous video. Let's look at the ARP process once more. So, PC1 makes this ARP request packet. The source IP is its own IP address, and the destination is R1's G02 interface, which is the default gateway configured on PC1. Next is the MAC addresses. This is a minor point, but note that I put the source IP before the destination IP, but the destination MAC before the source MAC. That's because in the IPv4 header, the source IP address comes first, but in the Ethernet header, the destination MAC address comes first. Anyway, just a minor point. The destination MAC address is the broadcast MAC address of all Fs, because it doesn't know the MAC address of R1, so it will send the frame to all hosts on the network. Finally, the source MAC address is its own MAC address. So, it sends the frame, which switch 1 receives and broadcasts out of all its interfaces, except the one it received the frame on. In this example, only PC1 and R1 are connected to switch 1, so that means that switch 1 will forward the frame out of its G00 interface. To translate the meaning of this frame into English, PC1 is basically saying, "Hi, 192.168.1.254, what's your MAC address?" Although I'm not going to really talk about the switches much in this video, note that switch 1 learns PC1's MAC address on its G01 interface when the frame arrives on its G01 interface. When this broadcast frame arrives in R1, it notices that the destination IP is its own IP, so it creates this ARP reply frame to send back to PC1. Although the ARP request message was broadcast, because R1 learned PC1's IP and MAC addresses from the ARP request message, the ARP reply can be sent unicast directly to PC1. So that's what R1 does. To translate this ARP reply message into English, basically it means, "Hi 192.168.1.1, this is 192.168.1.254. My MAC address is AAAA." Note that switch 1 will learn R1's MAC address from this message when the frame arrives on its G00 interface. So, now PC1 knows the MAC address of its default gateway, so it encapsulates the packet with this Ethernet header. Keep in mind, the original packet is not changed. The destination address remains PC4's IP address, not R1's IP address. Only at layer 2 is the destination set to R1's MAC address. So, it sends the frame to R1. R1 receives it and removes the Ethernet header. It looks up the destination in its routing table. The most specific match is this entry for the 192.168.4.0/24 network, which specifies a next hop of 192.168.12.2. So, R1 will have to encapsulate this packet with an Ethernet frame with the appropriate MAC address for 192.168.12.2. However, R1 doesn't know R2's MAC address yet, so how will it learn R2's MAC address? It will use ARP, of course. The source IP address of this ARP request will be R1's, and the destination will be R2's. The destination MAC address is all F's, the broadcast MAC address, because R1 doesn't know R2's MAC address, and the source is BBBB, which is the MAC address of R1's G00 interface. So, it sends the ARP request, and R2 receives it. Basically, what this ARP request says is, "Hi 192.168.12.2, what's your MAC address?" R2 receives the broadcast, and since the destination IP address matches its own IP address, it makes this ARP reply to send to R1. Once again, because it learned the IP and MAC addresses of R1 from the ARP request, it doesn't have to broadcast the frame. So it sends this ARP reply back, which basically says, "Hi 192.168.12.1, this is 192.168.12.2. My MAC address is CCCC." Okay, now R1 knows R2's MAC address, so it can encapsulate the packet with an Ethernet header, inserting R2's MAC address in the destination field, and the MAC address of R1's G00 interface in the source field, and it sends it to R2. After receiving the frame, R2 removes the Ethernet header. R2 then looks up the destination IP address in its routing table, and the most specific match, is this one for 192.168.4.0/24, with a next hop of 192.168.24.4. Although 192.168.24.0/24 is a connected network to R2, it doesn't know the MAC address of R4. So, you know what's next. R2 will use ARP to discover R4's MAC address. R2 prepares this ARP request frame using its own IP and MAC addresses for the source, R4's IP address as the destination, and the broadcast MAC address, and it forwards it out of its G01 interface. With this ARP request, R2 is saying, "Hi 192.168.24.4, what's your MAC address?" R4 receives the broadcast, and since the destination IP address is its own, it creates this ARP reply frame to send back to R2. Once again, it already knows R2's IP and MAC addresses, because they were used as the source addresses for the ARP request. It sends the unicast frame back to R2. With this ARP reply, R4 is saying, "Hi 192.168.24.2, this is 192.168.24.4. My MAC address is EEEE." Now that R2 knows R4's MAC address, it encapsulates PC1's packet with an Ethernet header with a destination MAC address of EEEE, which is R4's G01 interface, and a source MAC address of DDDD, which is R2's G01 interface. R4 receives the frame and removes the Ethernet header. It looks up 192.168.4.1 in its routing table, and the most specific match is this entry for 192.168.4.0/24, which is directly connected via the G02 interface. But once again, R4 doesn't know PC4's MAC address yet, so you know what it has to do next. It will use ARP to learn PC4's MAC address. It prepares this ARP request frame. Again, the source IP and MAC addresses are its own, the destination IP address is PC4's, and the destination MAC is the broadcast MAC address of all Fs. It sends this message out of its G02 interface, saying, "Hi 192.168.4.1, what's your MAC address?" Note that switch 4 will learn R4's MAC address on its G00 interface from the source MAC address field of this Ethernet frame. After PC4 receives the frame, it checks the destination IP address. Since it is its own IP address, it will send an ARP reply. The ARP reply will be unicast, using PC4's IP and MAC addresses for the source, and R4's IP and MAC addresses for the destination. It sends the frame out of its network interface, saying, "Hi 192.168.4.254, this is 192.168.4.1. My MAC address is 4444. Note that switch 4 learns PC4's MAC address when it arrives on its G01 interface. Now that R4 knows PC4's MAC address, it adds an Ethernet header to the packet, using its own MAC address on the G02 interface as the source address, and PC4's MAC address as the destination. R4 sends the frame to PC4, and finally it has reached its destination. Notice that the original packet hasn't changed throughout the process. It's always used the same IP header, with a source IP address of 192.168.1.1 and a destination IP address of 192.168.4.1. Also, notice that the switches didn't actually modify the frames at any point. The switches forwarded the frames and learned the MAC addresses, but they don't actually de-encapsulate and then re-encapsulate the packet with a new Ethernet header. Okay, now let's say PC4 sends a reply back to PC1, and we've configured static routes on the routers so that the traffic follows the same path on the way back to PC1, going via switch 4, R4, R2, R1, switch 1, and then reaching PC1. What will be different? First off, there will be one major difference. Since these devices have already gone through the ARP process, there won't be any need for ARP requests and replies. The packet will simply be forwarded from device to device, being de-encapsulated and then re-encapsulated as it is received by and then forwarded by each router. So, that's it. just a basic walkthrough of how a packet is forwarded between routers to pass it along to its final destination. Now, as for today's quiz, I'll do something different than usual. Instead of having multiple choice questions as usual, we'll use this same diagram to test your understanding. Let's get started with the quiz. Here's question 1. PC4 sends a packet to PC1. What is the destination MAC address when it is sent from PC4's network interface? Pause the video to think about your answer. The answer is FFFE, which is the MAC address of R4's G02 interface. That's because to send the packet to PC1, which is in a remote network, PC4 must send the packet to its default gateway, R4, first. To do that, it encapsulates the packet with an Ethernet header, with its default gateway's MAC address as the destination. Okay, let's go to question 2. PC4 sends a packet to PC1. What is the source MAC address when it is received on R1's G00 interface? Pause the video to think about your answer. The answer is CCCC, which is the MAC address of R2's G00 interface. When R2 sends the packet to R1 en route to its destination, PC1, it encapsulates the packet with an Ethernet header using its own MAC address as the source MAC address. Okay, let's go to question 3. PC4 sends a packet to PC1. What is the source MAC address when it is sent from switch 1's G01 interface? Pause the video to think about your answer. The answer is AAAA, which is the MAC address of R1's G02 interface. Switch 1 doesn't alter the frame to use its own MAC address. It simply forwards the frame out of the correct interface, or floods it if it doesn't know the destination. Let's go to question 4. PC4 sends a packet to PC1. What is the destination IP address when it is sent from R4's G01 interface? Pause the video to think about your answer. The answer is 192.168.1.1, which is the IP address of PC1. Although each router modifies the source and destination MAC addresses in the Ethernet header as it forwards the packet, they don't modify the original packet itself, so the destination IP address won't change. Since PC4 is sending the packet to PC1, that means the destination will be PC1's IP address, 192.168.1.1. Let's go to question 5. PC4 sends a packet to PC1. What is the source IP address when it is received on R1's G00 interface? Pause the video to think about your answer. The answer is 192.168.4.1, which is the IP address of PC4. As I said in the last question, the original packet is not modified as the routers forward it to its destination. So through the whole route, the source IP address remains PC4's IP address, 192.168.4.1. Okay, for this video there will once again be supplementary materials to help you practice what you've learned. There will be a Packet Tracer practice lab, in which you use Packet Tracer's simulation mode to analyze a packet and test your knowledge and understanding. That will be the next video. And that's it. There won't be a flashcard deck for this video, since there wasn't actually any new information in this video. However, if there are some new points that you picked up in this video, feel free to make your own flashcards. Actually, even though I make flashcard decks for each video, I also think it's a good idea to make your own flashcards too, if there is anything else you want to remember. You can also edit the flashcards I provide, or delete some flashcards if you think some of them are not necessary. The flashcards are just a tool to help you, so feel free to use them however you think is best. Okay, that's all for today's video. Good luck with your studies. Thank you for watching. Please subscribe to the channel, like the video, leave a comment, and share the video with anyone else studying for the CCNA. If you want to leave a tip, check the links in the description. I'm also a Brave verified publisher and accept BAT, or Basic Attention Token, tips via the Brave browser. That's all for now.